In September 2013, a rocket named Antares lifted off from Wallops Island, Virginia, carrying supplies to the International Space Station. It was an American rocket built by a company from the States, launching a US mission. But at the heart of that rocket, providing the raw power to escape Earth's gravity, were two engines that told a very different story. They were designed in the Soviet Union, built in the 1960s, created for a moon mission that never succeeded, hidden in secret for decades, and resurrected by the very country they were meant to help defeat. This is the story of the NK-33, one of the most efficient rocket engines ever built, conceived at the height of the Cold War, lost to history, and rediscovered in one of the strangest technological second acts you've ever heard. It's a story about engineering brilliance, political collapse, and one of the greatest ironies of the space age, and how the Soviet Union's failed attempt to reach the moon eventually helped America reach orbit. Let's dig in. To understand the NK-33, we need to go back to the 1960s, a time when the Cold War wasn't just about nuclear arsenals and espionage. It was also a race to prove technological supremacy through space exploration. When President Kennedy announced in 1961 that America would put a man on the moon before the decade ended, it wasn't just a scientific goal, it was a challenge. And the Soviet Union, which had already beaten the US to space with Sputnik and the first human in orbit, wasn't about to back down. The Soviets had every reason to believe they could win. After all, they had launched the first satellite in 1957. They had sent the first living creature to space, a dog named Laika. They had put Yuri Gagarin into orbit in 1961, making him the first human in space. They had achieved the first spacewalk with Alexei Leonov in 1965. By almost every measure, the Soviet space program was ahead. The moon seemed like the natural next victory. The Soviets needed their own moon rocket. That rocket became the N-1. The N-1 was the Soviet Union's answer to NASA's Saturn V. It stood nearly 105 meters tall, slightly taller than the Saturn V, and was designed to carry cosmonauts to the moon and back. The rocket was designated N-1, where N stood for Nositel, meaning carrier in Russian. It was also sometimes called Hercules in internal documents, reflecting the mythological scale of the ambition. The N-1 was absolutely massive. At full load, it weighed over 2,750 metric tons. It had 5 stages in total, though the first stage alone accounted for most of the drama in its story. But there was a fundamental difference in how these two superpowers approached the engineering challenge. The Saturn V's first stage used 5 massive F1 engines, each producing over 1.5 million pounds of thrust. 5 engines, proven, powerful, manageable. The N-1's first stage, 30 engines. You heard that right, 30 NK-15 engines, later improved into what became the NK-33, all firing simultaneously, producing a combined thrust of over 10 million pounds. Think about that for a moment. 30 individual rocket engines, each a complex machine with thousands of parts, all mounted in a circular configuration around the base of the rocket. Each one needed to ignite at precisely the right moment. Each one needed to produce the correct amount of thrust. Each one needed to be monitored, controlled, and coordinated with the other 29. Why 30 engines instead of 5? The answer is both practical and political. The Soviets didn't have a single engine large enough to match the F-1's power, and developing one would take time they didn't have. The F-1 engine was an engineering marvel in its own right, the most powerful single-chamber rocket engine ever built. But developing something that large required specific infrastructure, huge test stands, specialized manufacturing facilities, and years of iterative testing. The Soviet Union had a different constraint. Their rocket development facilities were located inland, far from ocean ports. This meant that any rocket component had to be small enough to transport by rail. The tunnels, bridges, and clearances of the Soviet rail system imposed a hard limit on the size of any single piece of hardware. So instead of one giant engine, chief designer Sergei Korolev and the Kuznetsov Design Bureau chose a different path: cluster many smaller, highly efficient engines together. This approach had theoretical advantages. If one engine failed, the others could potentially compensate, a concept called engine-out capability. The smaller engines were also easier to test individually, and by using many copies of the same engine, you could theoretically benefit from mass production and reliability improvements. On paper, it was ingenious. In practice, it created an engineering nightmare. Coordinating 30 engines created problems that had never been solved at this scale. Each engine had to be mounted on a gimbal system so it could swivel for steering. The rocket's guidance computer had to monitor the performance of all 30 engines in real time. If one engine underperformed, overperformed, or failed entirely, the computer had to adjust the thrust and gimbal angles of the remaining engines instantly. Otherwise, the rocket would tumble out of control. The vibrations from 30 engines firing created resonance problems that were difficult to predict. Fuel had to flow to all 30 engines through a complex network of plumbing. A blockage, leak, or pressure variation in any one feed line could trigger a cascade of failures. And remember, this was the 1960s. The computers available to the Soviets were primitive by modern standards, large, slow, and limited in processing power. The control algorithms had to be simple enough to run on that hardware, yet sophisticated enough to manage an incredibly complex system. Before we get to what went wrong, let's talk about what went incredibly right. The NK-33 wasn't just another rocket engine. It represented a technological leap that, in many ways, the United States wouldn't match for decades. Let's break down why. The NK-33 burned RP-1, essentially highly refined kerosene and liquid oxygen. This is a common rocket fuel combination, used because it's relatively stable, energy-dense, and easier to handle than alternatives like liquid hydrogen. Liquid hydrogen, while more efficient, is extremely cold, -253 degrees Celsius, difficult to store, and has very low density, requiring enormous fuel tanks. RP-1 is much denser, can be stored at more manageable temperatures, and has been used in rockets since the early days of spaceflight. The downside is that kerosene produces lower specific impulse than hydrogen. But for a first-stage engine, where density and thrust matter more than ultimate efficiency, kerosene is often the better choice. Here's where things get interesting. Most rocket engines use what's called a gas generator cycle. Let me explain how that works. In a gas generator engine, a small amount of fuel and oxidizer is burned in a separate chamber called, appropriately, a gas generator. This creates hot gas that drives a turbine, which powers pumps that push fuel and oxidizer into the main combustion chamber at high pressure. After driving the turbine, that gas is either dumped overboard through a separate nozzle or burned at the engine's periphery. It's simple, reliable, and effective. The F1 engine on the Saturn V used this cycle, but it's also inefficient. The gas used to drive the turbopumps is essentially wasted. It's not contributing its full potential energy to thrust. You're burning maybe 3 to 5% of your propellant just to run the pumps. And because the turbine can't handle extremely hot gas, you have to run the gas generator fuel, rich with excess fuel to cool the exhaust, which further limits efficiency. The NK-33 used something far more advanced, oxygen-rich staged combustion. In this cycle, fuel and oxygen are burned in a pre-burner at extremely high pressure, but instead of dumping the exhaust, that oxygen-rich gas, still packed with energy, drives the turbopumps at tremendous speed. Then, after powering the turbines, that same gas is injected into the main combustion chamber where it meets additional fuel and burns again. Nothing is wasted. Every bit of energy is extracted. The result is exceptional efficiency. You're burning all your propellant in the main chamber, extracting maximum energy. You can run much higher chamber pressures because your turbopumps are spinning faster. Higher pressure means better combustion efficiency and higher performance. But there's a catch, a big one. Oxygen-rich gas at high temperature and pressure is incredibly corrosive. At the temperatures inside a turbopump driven by oxygen-rich gas, most metals will literally burn. Oxygen is an oxidizer. It wants to react with things. When you combine it with heat, pressure, and high-speed turbine blades made of metal, you're essentially creating conditions where the engine wants to destroy itself from the inside. American engineers in the 1960s looked at oxygen-rich staged combustion and decided it was too difficult, too dangerous, and too expensive to pursue. The technical challenges seemed insurmountable. What materials could withstand that environment? How do you prevent the turbine blades from oxidizing and failing? How do you seal components when everything is under extreme pressure and temperature? NASA chose to focus on what they knew worked: gas generator cycles for kerosene engines and simpler staged combustion for hydrogen engines. The Soviets solved it. Through advanced metallurgy, precision manufacturing, and sheer engineering determination, Kuznetsov's team built turbopumps and combustion chambers that could withstand the hellish conditions inside an oxygen-rich staged combustion engine. They developed special alloys and coatings. They engineered turbine blade geometries that could handle the stress. They created sealing systems that worked under extreme conditions. And they tested, failed, redesigned, and tested again until it worked. It took years of development, countless setbacks, and the resources of a superpower determined to win the space race. But they did it. Let's talk performance. Weight, approximately 1,250 kilograms. Thrust, 1.51 meganewtons, about 340,000 pounds force at sea level, 1.75 meganewtons, 392,000 lbf in vacuum. Specific impulse, around 331 seconds in vacuum. That last number, specific impulse, is critical. It's a measure of efficiency, how much thrust you get per unit of propellant. Think of it like fuel economy in a car. Higher specific impulse means you get more performance from the same amount of fuel. For a kerosene engine, 331 seconds is exceptional. Even today, few engines match it. Modern kerosene engines typically range from about 300 to 340 seconds in vacuum. The NK-33, designed in the 1960s, sits at the high end of that range. The NK-33 also had one of the highest thrust-to-weight ratios ever achieved. Thrust-to-weight ratio is exactly what it sounds like: how much thrust the engine produces compared to how much the engine itself weighs. A higher ratio means you're getting more power from less mass, which is critical in rocketry, where every kilogram matters. At the time of its development, it held the world record for chamber pressure in a production rocket engine. Higher chamber pressure generally means better combustion efficiency. It's one of the key factors that determines engine performance. And it could gimbal swivel on its mount to steer the rocket. Each NK-33 could pivot several degrees in any direction. With 30 engines, the N1's first stage had tremendous control authority, at least in theory. All of this was built in the Soviet Union in the 1960s, with the manufacturing capabilities and tolerances of that era. It's widely reported among aerospace historians that the precision required to build these engines was extraordinary, pushing the limits of Soviet industrial capability. The tolerances on turbopump components were measured in microns. The welding had to be perfect. Any flaw could lead to catastrophic failure. The materials had to be precisely mixed and heat-treated. Every component had to be balanced and tested. This wasn't mass production in the modern sense. These engines were hand-built by highly skilled workers and engineers. Each one was essentially a custom machine. The NK-33 wasn't just good, it was world-class. It represented the absolute peak of what Soviet rocket engineering could achieve. But remember, the N1 didn't use one NK-33. It used 30 engines in its first stage alone. This created a monumental control problem. Imagine trying to balance the thrust of 30 rocket engines simultaneously, each producing hundreds of thousands of pounds of force, each with slight variations in performance, all while the rocket is accelerating, vibrating, and fighting against the stresses of launch. Even with perfect manufacturing, no two engines are completely identical. There will always be tiny variations in thrust, in fuel flow, in response time. Multiply that by 30, and you have a control system nightmare. If even one engine failed or underperformed, the others had to compensate instantly, or the rocket would spin out of control. And the system had to make these adjustments in milliseconds. To make matters worse, the Soviet Union never built a test stand large enough to fire all 30 engines together on the ground. This wasn't for lack of trying. A test stand for 30 NK-33 engines would have been an enormous undertaking. The thrust forces alone would require massive concrete structures anchored deep into the earth. The fuel supply system would have to deliver thousands of liters of RP1 and liquid oxygen per second. The acoustic energy, the sheer noise from 30 engines would be devastating to nearby structures, and the cost and time required to build such a facility competed with the pressure to launch quickly and beat the Americans. So the decision was made to skip full-stack testing. Every N1 launch was, in effect, the first full-scale test of that particular configuration. The Saturn V, by comparison, was exhaustively tested. Every stage, every engine, on the ground, again and again. NASA's philosophy was test, 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 then test again. Component tests, engine tests, stage tests, full vehicle tests. Only after hundreds of firings and thousands of hours of data analysis did the Saturn V fly. And when it did fly, it worked. The N1 followed a different path, not by choice, but by necessity. Between 1969 and 1972, the Soviet Union launched 4 N1 rockets. All 4 failed. Let's look at each one. The first N1 lifted off from the Baikonur Cosmodrome in Kazakhstan. For the first minute, it seemed to be working. All 30 engines ignited. The rocket climbed. Then, 68 seconds into flight, a fire broke out in the engine compartment. The fire was caused by a propellant leak that ignited. Vibrations from the 30 engines had likely caused a fuel line to crack. The rocket's control system detected the problem and began shutting down engines to prevent the fire from spreading. But shutting down engines in flight meant losing thrust asymmetrically. The rocket began to tumble. At 70 seconds, the automatic destruct system activated and the rocket exploded. The entire mission lasted less than 2 minutes. This one is particularly tragic in terms of timing. It launched just 13 days before Apollo 11 left for the moon. The Soviets knew they were running out of time. This second N1 was supposed to prove that the design could work. The rocket lifted off. All 30 engines were running. Then, just seconds into flight, there was a catastrophic explosion. A piece of debris, possibly a loose bolt or a metal fragment, was sucked into one of the liquid oxygen turbo pumps. The pump disintegrated. The engine exploded. The explosion triggered a chain reaction. Adjacent engines failed. The rocket fell back onto the launch pad and exploded in what remains one of the largest non-nuclear explosions in history. The blast was estimated at the equivalent of 7,000 tons of TNT. It destroyed the launch complex, damaged facilities up to a kilometer away, and left a massive crater. Remarkably, there were no fatalities, though several people were injured. The launch complex took over a year to rebuild, and by the time it was ready, Apollo 11 had already landed on the moon. The Soviets didn't give up. Engineers redesigned components, improved control systems, and prepared a third attempt. This N1 actually performed better than the previous 2. It flew for nearly 51 seconds before encountering problems. The rocket began to roll uncontrollably around its vertical axis. The control system tried to correct by gimballing the engines, but the roll rate was too high. Structural loads exceeded the rocket's design limits, and it broke apart. The cause was later determined to be unexpected resonance and vibration modes that the control system couldn't compensate for. Again, the complexity of managing 30 engines had created a failure mode that was difficult to predict or prevent. The fourth and final N1 launch was the most successful and perhaps the most frustrating. This time, the rocket flew for 107 seconds. It cleared the tower, it climbed, the engines were working. For a brief moment, it seemed like the N1 might actually succeed. Then an engine fire developed in the first stage. The cause was a faulty turbopump in one of the NK-15 engines. The fire damaged surrounding engines and structures. The control system shut down the first stage, but by then the damage was done. The rocket crashed into the steppes of Kazakhstan. So close, yet still a failure. Engine-related issues, plumbing failures, control system problems, vibration contributed to several of these disasters. But here's an important nuance. The NK-33 engines themselves were not fundamentally flawed. When tested individually on test stands, the engines performed beautifully. They met their specifications, they ran reliably, they demonstrated the performance that the engineers had promised. The failures were largely systemic issues with controlling so many engines at once, with quality control across a massive supply chain, and with integrating an enormously complex vehicle without adequate testing infrastructure. Think of it this way: each NK-33 was a masterpiece. But trying to coordinate 30 masterpieces simultaneously with 1960s computer technology without full-scale ground testing turned out to be a bridge too far. The engines, when tested individually, performed beautifully, but the N1 as a whole never succeeded. In 1974, after spending billions of rubles and suffering repeated failures, and after the United States had already won the moon race, the Soviet government officially cancelled the N1 program. By this point, Apollo 11 through Apollo 17 had been to the moon. 12 Americans had walked on the lunar surface. The race was over, and the Soviets had lost. Continuing the N1 program served no political purpose. And then came the order: destroy all remaining hardware. Rocket stages, fuel tanks, electronics, launch pads and engines, everything. The Soviet leadership wanted no evidence of the failure, no reminders of the program that couldn't beat America. This was typical of Soviet secrecy culture. Failures were not acknowledged publicly. Evidence was erased. The N1 program was classified, and the world wouldn't know the full story for decades. Workers began dismantling the infrastructure, cutting up metal, scrapping components. Valuable equipment that had cost fortunes to develop was being destroyed for political reasons. But Nikolai Kuznetsov, the chief designer behind the engines, made a different choice. Kuznetsov and his team knew something the politicians didn't fully appreciate: the NK-33 was a masterpiece. Yes, the N1 failed, but the engines themselves represented years of research, testing, innovation, and problem-solving. They were some of the most advanced rocket engines on Earth. Destroying them would be an act of technological vandalism. So, quietly, Kuznetsov's engineers disobeyed the order. This was not without risk. Disobeying a direct government order in the Soviet Union could have serious consequences, but the engineers believed the technology was too valuable to lose. Instead of destroying the engines, they carefully preserved them. They were cleaned, sealed, protected from corrosion, and stored in warehouses in Samara, Russia, the city where the Kuznetsov Design Bureau was based. Special protective coatings were applied to prevent oxidation. The engines were wrapped and sealed to keep out moisture and contaminants. Documentation was preserved: technical drawings, test data, manufacturing procedures. It's widely reported that dozens of engines were saved this way. Some sources suggest the number was around 40 to 50 engines, though exact figures remain unclear. Not all NK-33s were saved. Some were indeed destroyed as ordered, but a significant number survived. And then, for nearly 2 decades, they sat in darkness. The NK-33 design remained classified. The West didn't know these engines existed. Even within the Soviet Union, knowledge of the hidden engines was limited to a small circle of engineers. Most of the world forgot about the N1 entirely. The engines that were supposed to beat America to the moon became a Cold War secret hidden in Russian storage. The irony is remarkable. While American engineers were developing new rocket engines through the 1980s, the Soviets had a stockpile of advanced engines sitting unused. Engines that, in many ways, were more sophisticated than what the Americans were flying. But politics and secrecy kept them hidden. Fast forward to 1991. The Soviet Union collapsed. The Cold War ended. Russia's economy plunged into crisis. The ruble lost value. State budgets evaporated. Salaries went unpaid. Aerospace companies that had once been funded by a superpower were suddenly scrambling for money. Engineers and scientists faced unemployment. Entire design bureaus were at risk of closing. State secrets were no longer strategic assets. They were potential products. If selling technology to the West could keep the lights on and pay salaries, then that's what would happen. Russian firms began approaching the West, offering technology, expertise, and hardware for sale. Rocket engines, satellite systems, manufacturing knowledge. Things that would have been unthinkable just a few years earlier were now on the table. And that's when the rumors started. In the mid-1990s, representatives from the Kuznetsov Design Bureau reached out to Western aerospace companies with an extraordinary claim. We have rocket engines from the 1960s, High performance, oxygen-rich staged combustion, kerosene engines, still in storage, still functional. To American engineers, this sounded almost absurd. Rocket engines from the 1960s, Soviet engines? That had been sitting in a warehouse for 20-plus years? And they're supposed to still work? The Cold War had ended, but skepticism remained. Soviet technology was often viewed as crude, heavy, and behind Western standards. The idea that the Soviets had built engines more advanced than American designs seemed unlikely. But Aerojet, a major US aerospace company, decided to investigate. Aerojet had been in the rocket engine business since the 1940s. They knew what good engineering looked like, and the claims about oxygen-rich staged combustion caught their attention. Because by the 1990s, American engineers had finally begun to appreciate just how valuable that technology was. When Aerojet's team arrived in Samara, they found something that defied expectations. Rows of NK-33 engines, still sealed, preserved in protective wrappings. The storage conditions were crude by Western standards, but the engines themselves were intact. American engineers inspected them. They reviewed technical documents, performance data, design schematics. They examined the turbopumps, the combustion chambers, the gimbal systems, and they were stunned. These weren't just functional engines. They were exceptional engines. Engines using technology, oxygen-rich staged combustion, that the United States had only recently begun to master. The specific impulse numbers were impressive. The thrust-to-weight ratio was extraordinary. The chamber pressure was higher than most American engines of that era. And all of this had been achieved in the 1960s. Aerojet's engineers asked questions, ran calculations, studied the designs. Everything checked out. These engines were the real deal. Aerojet negotiated a deal. They purchased approximately 36 NK-33 engines. The price was remarkably low by aerospace standards, a few $1 million for the entire lot. For the Russian Design Bureau, it was desperately needed funding. For Aerojet, it was an opportunity to acquire world-class hardware at a fraction of what it would cost to develop equivalent engines from scratch. Then came the real test. Back in the United States, Aerojet prepared one of the NK-33 engines for a test firing. The engine had been built in the late 1960s or early 1970s. It had been stored for more than 2 decades. It had never flown in a successful mission. Would it even start? There was genuine uncertainty. Rocket engines are complex machines with thousands of precisely manufactured parts. Seals can dry out, metals can corrode, tolerances can shift. Even under ideal storage conditions, there's no guarantee a decades-old engine will work. And these hadn't been stored under ideal conditions, just preserved as best as the Russian engineers could manage. The test firing was conducted in the late 1990s at a test facility in the United States. Engineers monitored every sensor, every pressure reading, every vibration. Fuel and oxidizer lines were connected. The engine was mounted on a test stand designed to measure thrust. High-speed cameras were positioned to observe the ignition and combustion. The countdown began. The ignition sequence began. Propellants flowed. The igniters fired. The engine fired. Not only did it worked flawlessly. It met every performance specification. The thrust was exactly as predicted. The efficiency matched the original Soviet data. The combustion was stable, no vibrations, no anomalies. The turbopumps operated smoothly at their extremely high rotational speeds. The engine ran through its full test duration without a single issue. When the test ended and the data was analyzed, American engineers were astonished. Here was a rocket engine designed 3 decades earlier, stored under conditions far from ideal, and it performed as if it had rolled off the production line yesterday. NASA conducted additional tests. The results were confirmed again and again. Different engines from the lot were fired. They all performed as specified. NASA engineers examined the design in detail. They studied the metallurgy, the combustion dynamics, the turbopump engineering. The more they learned, the more impressed they became. The NK-33 wasn't just good. It was, in many measurable ways, superior to comparable American engines of the same era and competitive with modern designs. The specific impulse was at the top end of what kerosene engines could achieve. The thrust-to-weight ratio was exceptional. The reliability based on test firings was excellent. This was technology the United States had tried to develop and largely given up on in the 1960s. And the Soviets had not only succeeded, they had succeeded brilliantly. Aerojet refurbished the engines for use in American rockets. The refurbishment included updated wiring and electrical connectors compatible with US voltage standards and control systems, modern sensors compatible with American data acquisition systems, new gimbal actuators for steering integration with Western guidance computers, safety and quality inspections to meet NASA standards, replacement of any seals or components that showed age-related degradation. The refurbishment process was extensive, but nowhere near as expensive as developing new engines. Each engine was essentially brought up to modern operational standards while preserving the core Soviet design. Once refurbished, the engines were rebranded as the AJ-26. The designation followed Aerojet's naming convention. But make no mistake, underneath the new label, these were NK-33 engines through and through. The combustion chamber, the turbopumps, the fundamental design, all Soviet. They passed multiple test firings. They were certified for flight. And then came the question, what rocket would use them? In the 2000s, NASA was looking for commercial partners to resupply the International Space Station. After the Space Shuttle's retirement was announced, NASA needed alternative ways to deliver cargo to the ISS. The Commercial Orbital Transportation Services Program was created to encourage private companies to develop cargo delivery capabilities. One of the companies selected was Orbital Sciences Corporation, later Orbital ATK, now part of Northrop Grumman. Orbital was developing a new medium-lift rocket called Antares. For the first stage, they needed powerful, reliable engines. Developing a brand new rocket engine would cost tens of millions of dollars and take years. The economics of rocket development are brutal. Engine development requires extensive testing, multiple iterations, certification and qualification. A modern rocket engine development program can easily cost $200 to $500 million and take a decade. For a commercial company trying to win a NASA contract, that timeline and cost were prohibitive. But Aerojet had a solution. The AJ-26. Surplus Soviet engines, refurbished and ready. Cost, approximately $1 million per engine, roughly 1/10 the cost of developing new engines. The performance was proven. The technology was mature. From a business perspective, it was almost too good to be true. Orbital Sciences made the deal. The Antares rocket would use 2 AJ-26 engines on its first stage to launch the Cygnus cargo spacecraft to the ISS. It was an American rocket with a Soviet heart. The first Antares launch using AJ-26 engines occurred in April 2013. It was a test flight, and it succeeded. The engines performed exactly as predicted. The rocket reached orbit. All systems worked. It was a validation not just of the Antares design, but of the entire concept of using refurbished Soviet engines. More missions followed. September 2013. First operational cargo mission to the ISS, successful. January 2014, successful resupply mission delivering experiments and supplies. July 2004, another successful flight. Each mission delivered several tons of cargo to the International Space Station. Food, water, scientific experiments, spare parts, crew supplies. The engines performed exactly as expected. Decades after they were built to take cosmonauts to the moon, NK-33 engines were helping America resupply the International Space Station. The irony was complete. The same engines designed to beat America in the space race were now helping maintain America's presence in space. Engineers from both countries had come together, not as rivals but as partners, to make it happen. It was, in a strange way, a happy ending to the N1's story. The engines finally got to fly successful missions. They finally got to contribute to space exploration, just not in the way anyone had originally planned. Then came the failure. On October 28, 2014, an Antares rocket lifted off from Wallops Island, carrying a Cygnus spacecraft loaded with supplies. The mission was designated Orb 3. The spacecraft carried over 2,200 kilograms of cargo, including food, scientific experiments, and equipment for the ISS crew. 15 seconds after liftoff, there was an explosion. The rocket's first stage failed catastrophically. The vehicle broke apart and crashed back onto the launch pad, destroying the rocket, the cargo, and the launch facility. The explosion was captured on video and witnessed by spectators who had gathered to watch the launch. Fortunately, no one was injured, but the loss was significant. The investigation traced the failure to a turbo pump in one of the AJ-26 engines. Specifically, a component in the liquid oxygen turbo pump had failed, likely due to age-related fatigue or refurbishment issues. Remember, these engines were 40-plus years old at the time of the failure. Even with refurbishment, there are limits to how much you can rejuvenate aging hardware. Metals fatigue. Microscopic cracks can develop. Stresses accumulate over decades. The specific failure mode involved a component that had passed inspection and testing, but failed under the extreme conditions of flight. It's worth noting, this was not a common failure mode in the original NK-33 design. The failure wasn't a fundamental design flaw. The NK-33 design itself remained sound, but the reality of using hardware that old, even with refurbishment, had caught up. Orbital ATK faced a decision. They had additional AJ-26 engines in inventory, but the investigation had revealed the risks of using such old hardware. Could they trust the remaining engines? Orbital ATK made the decision to replace the AJ-26 engines. Interestingly, they replaced them with another Russian engine, the RD-181, a modern engine produced by NPO Energomash, a different Russian design bureau. The RD-181 also uses oxygen-rich staged combustion technology pioneered by Soviet engineers and proven successful in engines like the RD-170 family and the RD-181 used on the American Atlas V rocket. So, even after the NK-33's operational life ended, America's reliance on Soviet-era staged combustion technology continued. The RD-181 was newer, produced with modern manufacturing, and came with support and quality assurance from the manufacturer. Antares was redesigned to accommodate the new engines. It returned to flight in 2016 and has flown successfully since. But the era of the NK-33 in American service was over. Despite the 2014 failure, the NK-33's legacy is undeniable. It is widely considered one of the most efficient kerosene rocket engines ever built. Even today, few engines match its specific impulse and thrust-to-weight ratio. It demonstrated that oxygen-rich staged combustion, once thought too dangerous by American engineers, was not only possible but superior in performance. That lesson changed American rocket engine development. Modern American engines, like SpaceX's Raptor engine, use staged combustion. Blue Origin's BE-4 engine uses oxygen-rich staged combustion. The technology that seemed impossible in the 1960s is now the gold standard, and the NK-33 proved it could work. The NK-33 became a teaching tool. After the Soviet collapse, Russian aerospace engineers studied the preserved engines to understand the manufacturing techniques and design principles of an earlier generation. In a very real sense, the hidden engines helped preserve institutional knowledge that might otherwise have been lost. When experienced engineers retired or passed away, the hardware remained as a physical record of their expertise. The NK-33 story didn't end entirely with Antares. A variant called the NK-33-1 was used on Russia's Soyuz 2-1V rocket, a small launcher designed for light payloads. The Soyuz 2-1V flew successfully from 2013 to 2022, giving the NK-33 design a final decade of operational life. The last flight of an NK-33 variant occurred in 2022, nearly 60 years after the engine was first designed. That's an extraordinary operational lifespan for any aerospace technology. For context, the Boeing 747 first flew in 1969 and is being phased out now. The NK-33 was designed in that same era and was still flying operational missions in 2022. But the NK-33's legacy goes beyond engineering. It's a story about what happens when politics and engineering collide. The N-1 program failed, not because Soviet engineers lacked skill, but because the program was under-resourced, rushed and burdened by systemic issues, including the lack of adequate testing infrastructure. The NK-33 succeeded because brilliant engineers, working under immense pressure, created something exceptional, and then politics nearly destroyed it. If Kuznetsov and his team had followed orders, those engines would have been scrapped. The technology would have been lost. The United States would never have had the option to use them. Instead, a quiet act of defiance, hiding engines in a warehouse, preserved a piece of technological history. It's a reminder that sometimes the most important decisions are made not by politicians or generals, but by engineers who understand the value of what they've created. There's a profound irony here. The Soviet Union spent billions trying to beat America to the moon. They failed. But decades later, their moon rocket engines helped America maintain access to space. The country that built the NK-33 no longer exists. The moon mission it was designed for never happened. But the engines themselves outlasted the Soviet Union, outlasted the Cold War, and became a critical part of the very space program they were meant to defeat. It's one of the strangest technological inheritances in history. And it raises an interesting question. How much other remarkable technology was lost, destroyed, or forgotten because of political decisions? How many other NK-33s are out there, not literally, but metaphorically, waiting to be rediscovered? So what's the takeaway from all this? First, great engineering transcends politics. The NK-33 was a product of Cold War rivalry, but its value wasn't ideological. It was a tool, a brilliantly designed tool that worked regardless of who used it or why. American engineers didn't care that it was Soviet, they cared that it was good, and it was. Second, preservation matters. Kuznetsov's decision to save those engines was an act of faith in the future. He couldn't have known the Soviet Union would collapse. He couldn't have predicted that American companies would buy and fly his engines. But he knew they were worth saving, and he was right. Sometimes the most important thing you can do is preserve knowledge and technology for a future you can't predict. Third, technological competition drives innovation. The space race pushed both superpowers to attempt things that seemed impossible. The NK-33 exists because Soviet engineers were given an impossible deadline and refused to accept defeat. That competitive pressure, combined with institutional support and engineering freedom, created breakthroughs. We're seeing the same dynamic today with commercial space companies. Competition drives innovation. Finally, history is full of surprises. No one in 1974 could have imagined that Soviet moon rocket engines would one day power American missions to the International Space Station. No one in 1991 could have predicted that engines hidden in a warehouse would become a cost-effective solution for a 21st century space program. The story of the NK-33 reminds us that engineering, politics, and history don't follow straight lines. Sometimes the greatest achievements come from failures. Sometimes the most valuable technologies are the ones we almost threw away, and sometimes the engines built to win a race that was lost end up helping the winners reach even higher. The NK-33 is more than just a rocket engine. It's a monument to human ingenuity under pressure. It's proof that great ideas can survive political collapse, and it's a reminder that in engineering, like in history, the story is never really over. Those engines sat in the dark for 20 years, waiting, and when the world changed, they were ready. If you found this story as fascinating as I did, consider subscribing. We explore iconic engines from across history, engines that didn't just move vehicles, but moved the world. Thanks for watching. And remember, sometimes the most incredible machines are the ones we almost forgot existed.